start with the first presentation. You already see it's on your screens. The first project. Yeah, so I'll give the words to my colleagues.
Okay, that's me. My name is Alexey Semenov, or Alexey Semenov, and it's a great honor for me to participate in this conference. But also it's a great chance and opportunity for me and my group of researchers to have young, talented mathematicians to join our project and perhaps to obtain new advanced mathematical results in the field, and to be, extend our activities to have much more younger mathematicians participated in this. And so I just should indicate who are these people. It's not enough space here to show you all the faces, but that's me first, Alexey Semenov, or Alexey Semenov in Russian, Sergey Sopronov, who will participate via Zoom, and Boris Frankin, Ilya Ivanov-Pogadayev, Roman Isayev, and Vladimir Kondratyev. So the general procedure and the code of the conference you've had, and so I'm just going straight to the content. So the title of our project is Theory of Definability. So definability is the major notion in what we are going to do. And we just have a new screen. Yes, I know. Oh, yeah, okay. So to repeat it, we are going to have these days to introduce all the participants who will join our project to the project and to start the research. Of course, it would not be immediately the research of new issues. We'll start with just problems to solve for learning, but we believe that from some moment we really will pass to something really new. And we hope that we can have a progress at least two problems for which solution is not known, which is usually called in science open problems. And also we think that the participants of the projects will constitute the international school for the theory of definability, so a community which will devote some of its research and all the efforts to advance this field. And we think that after the end of the conference, the research will continue and we'll have a chance to publish the results in some of the leading mathematical journals. I myself is a member of National Academy of Sciences and head of department in the Moscow State University. And to say a little bit more about this theory of definability, just to mention a few famous mathematicians from Europe who were working in this field in the 19th century and beginning of 20th century. So to have a context for our project in the mathematics in general, let's consider what really is happening in mathematics, what mathematicians are doing. And so this is to prove some theorem in mathematics, to compute something, calculate a value, and to define a new notion. So define is the key word for our project. So of course we'll have some computations, we are going to prove something, but the very subject of research for us will be definability. We'll consider definitions. So in these considerations, we'll use also such fields of mathematics as logic, and logic gives us a language in which we define this or that property or relation. We look at geometry, and geometry has a very specific role in our project, because geometry helps us to construct transformations that preserve some of these properties or relations. And we'll have modern algebra. You understand, of course, algebra means not only the school algebra to solve equations and investigate functions, but also there is an abstract algebra. And for example, theory of lattices is part of this modern algebra, and we'll use this field of mathematics, of algebra, and construct Galois correspondence between definitions, what we say definability, and transformations in geometry. Let's start with an example to explain what we mean by definition or definability. Everybody remembers from primary or secondary school a notion of prime number, one of these oldest and most interesting enigmatic concepts in mathematics. So the number p is prime if it is divisible only by itself and or by 1. So the definition can be expressed a little bit more elaborated way as it used unary relation or predicate or property to be 1, the unit, and the binary relation to be divisible by. So what happened? We explained a relation, be a prime number, through two relations, to be 1 or equal to 1, and to be divisible by. So to show that it's not only about mathematics, but it has also some sense in other fields of human culture, in linguistics, let's consider the definition of to be a brother-in-law. Or in Russian, it's called dever. A brother-in-law is a brother of a husband. So we have a woman, she has a husband, and the husband has a brother. So how to explain what does it mean? Let's make it more detailed. A person A is a brother-in-law of person C. It means that there is such a person B, that B is the husband of C, and A the brother of B. So now again, we defined the property or relation to be a brother-in-law through another relations or properties to be a husband, to be brother. So I believe it's very clear enough that it's pretty simple and clear, and in the same way, basic notion in all mathematics, and not mathematics only. For example, famous linguist Anna Wierzbicka, she is Polish and Australian scientist, proposed some 65 concepts through which everything in the world in any language can be defined. So you can consider it's very surprising and striking. And it's interesting to investigate more, but we don't have time for this, so we're coming back to our mathematical research. And here is the first basic example, which we'll consider really seriously for a while. So let's consider an order on rational numbers, linear order. X1 is less than X2. Can we define something, another property, another relation, through this binary relation? I believe that among our members of the conference and probably members of our future project, there are some people who can really find this kind of example. So I'll wait just for some 45 seconds. And if somebody can, yes, we have, if somebody can start her or his microphone and say what can be an example of this property. Yeah, I can hear nothing because of possibly different reasons. Let me look to the participants, and Yeah, yeah. Perhaps my speaker was out. So if anybody can say something. Are you too shy, or you don't understand something? If you don't understand what is needed, please say it also aloud. If you have any question, also you can just ask a question. No. Okay, let's go further. An example of that definition can be definition of a ternary relation. Ternary means with three arguments to lie between x1, say, and x2. What does it mean that x3 is in between of two other rational numbers? Of course, it means that x2 is between x1 and x3 if these inequalities hold, or these inequalities hold. So it doesn't matter is x1 less than x3 or smaller, but x2 is in between them. Okay, then we have defined this between ternary relation through linear order relation, through the relation x1 is smaller than x2. So the basic question we are going to investigate, can the relation of order x1 is smaller than x2 be defined through a relation lie between? Again, I hope that somebody can propose an answer to this. Can it be defined backwards? We defined between through order, and can we define now order through or with between? Does anybody have any idea on this? Silence again. Yeah, also what I can say that I cannot see anybody. So all the participants don't have their cameras turned on. Just to check, can anybody turn camera on? Can we see anybody? Ma'am? No, we cannot. Okay, so let's go further. The answer to this basic question for this case we consider is no. We cannot define or explain relation to be smaller or linear order through relation between. Intuitively, it's pretty evident. And if you try to discuss it with your friends and some other mathematicians, even starting mathematicians, perhaps relatively soon you'll come to an idea that if you just reverse the order, if you just rotate rational numbers in this way, then the relation between will stay untouched. If something was between, it will be between. It is between now. But the original relation of order will not hold. So if x1 was small x2, it is not smaller to x2 now, in opposite. But relation happens to be true. Okay, so with this symmetry, we'll can prove this fact. Okay, so going further, we can indicate that the famous mathematician, geometer Felix Klein of 19th century defined any geometry by its transformation group. And it doesn't matter what means specifically a notion of group here, but the set of all transformations in which a relation is invariant. It helps in many considerations in geometry, in topology, in algebraic geometry, in affine geometry, but we have now this geometrical consideration when we reversed the rational numbers. So as an example of Felix Klein considerations, we can mention affine geometry, in which the basic relation, the basic property is that two segments have the same length and direction. And affine geometry can be defined as a set of transformations which keep this relation indicated here to be true. So the general questions we ask here for any relation is what are the transformations that preserve order? It's a relatively simple task, and we hope that you will solve it pretty fast working in our project. Again, what are the transformations that preserve the order of rational numbers? Simple. Then, what are the transformations that preserve between? So we understand, of course, that all transformations that preserve order will preserve between as well. And we know a transformation which preserves between, and it does not preserve order. Remember, it's a symmetry of line. And then we can have some more problems. First of which of them is what are the relations that can be defined using less? The relation less can be defined using less itself, evidently, it's trivial. The relation between can be defined through relation less, as we shown on the previous screen. If there exists any other relation, not less and not between, that can be defined through order? Again, it would be good to ask if some of you can have an idea on this. Again, yes. No sign of existence. And finally, we can generalize the situation. There could be an arbitrary relation, yes, unary, binary, ternary, any number of arguments, 100 arguments, and can look to what are the relations that can be defined through a given relation. And then we can introduce a pretty straightforward notion of equivalent relations. Equivalent relations are relations that the first one can be defined through the second one, and the second one can be defined through the first one. So this is the basic framework for all our considerations. And then if we go further, I'm not going to explain it in details in my talk now, don't have enough time, but the correspondence between transformation groups and the classes of relations or properties can be described as Galois correspondence. The Galois correspondence, and perhaps you will have more chance to work on this in your projects in our conference, usually considered as correspondence between algebraically closed fields, field extensions, and transformation groups. So the second basic example, and the last one in my talk, is succession of integer numbers. So relation given by formula y equals x plus 1. So again, the very basic question here, what can be defined? What are other relations you can define? Naturally, you can say, for example, that y equals x plus 2 can be defined. Not just immediately, but in just 1 or 2 steps, you find a way how to define x plus 2. And some other interesting relations can be defined. And then we're coming to an issue of how to prove that something is not definable. Again, we can invent some transformations for integers z, and discover that for some relations, we cannot prove that they are equivalent. Perhaps they are different, and one of them cannot be defined through another one, but we don't have enough transformations. We cannot find any transformation at all. And then we'll come to an idea of what can be called non-standard integers, how it's non-standard analysis and other fields of mathematics, which is kind of ideal elements in geometries. So now we are coming to the open problems, which I indicated in the beginning, and we hope that we can move to the direction of some solutions from these problems. And these are very similar to what we are described earlier, and which we solved earlier, and we are going to solve it together with you. And these are problems which are not solved yet, and in which we hope that you will help us to solve together. The first issue is rational numbers with addition. We have rational numbers with a relation less with an order, and here we have addition, which is, you can imagine, a ternary relation with 3 arguments, x plus y equals to z. We have some progress here and have some hypotheses how it can be solved, and we can discuss it with interesting participants interested in this from you. Another are natural numbers with order. We have integers with order, and instead of integers, we can have natural numbers, means say 0, 1, etc., or 1, 2, 3, etc. So these are the second open problem we propose for you to discuss. Yes, it's my mistake. Here it's really integers with order instead of integers with successor. Binary relation is binary relation of order. You understand what this is? And the third issue is natural numbers with successor. So there are 3 open problems. 2 of them are on the screen: rationals with addition, integers with order, and natural numbers with succession, with +1. So that's all, and we hope that many of you will participate in this project, and hope we'll solve some of the problems we will propose in the few next days, and then go to some open problems to investigate and together to produce new mathematical results. So thank you very much. That was my presentation.